Alright, let's talk about now about the shear stresses in beams, and this is our last topic for the part 2 of the flexural members. And just recall that for a beam, when loaded in member, I mean, loaded in flexure, sorry about that. Right, so if we have this beam and it's loaded in flexure, then at a section, if we cut a section right here, what we see is or the internal forces that we see are the moment and the shear, right? Okay, so previously what we calculated are the moment portion for the flexural stresses, and right now we are going to solve for the shear stresses in beams, uh, because there also exists shear stress in the internal forces. Okay, so right here in our lecture handouts in figure 7-5, we have a section cut, and it shows the internal shear force. Okay, now if we represent this shear force or this resultant shear force in terms of its stress distribution, so it will look something like this. Okay, so there are forces in each of the fibers or the planes. Okay, so you would notice that right here we have a smaller stresses value, and in the midpoint we have a larger stress value. Okay, so there is actually a variation in the profile. So if we check this one, this is the shear stress distribution profile. So in terms of profile, we have a maximum right here. We have a maximum shear at the centroid or the neutral axis, and we have a zero shear at the outermost surface. So that's the distribution of the shear stress. And now, how do we compute for the shear stress? We have the equation. Shear is equal to VQ all over IT. Okay, so here's our working equations for whatever shapes, where V stands for the internal shear force, and Q, this is the first moment of area, and the equation for Q is simply the area times the distance, actually the distance from the neutral axis to the centroid of that area. And the difference between this first moment of area to the moment of inertia is that for the moment of inertia, we call it, the equation is area times the square of this distance. Okay, so that's why the moment of inertia is actually referred to as the second moment of area. And this one is the moment of inertia, and this is the thickness. Okay, so that thickness refers to of course, the thickness where the distribution of, like for example here, so that thickness, that would be this width right here, because that's where the entire distribution, that's where the entire stresses acts. So if it is hollow, then only the thickness portion of that hollow section should be considered. Okay, not the hollow. Not the thickness or not the width of the hollow portion. Okay, so because of this profile, by the way, there would be a shear max, and we can also take the average right here. Now, regarding the shear max, I have included in our lecture handouts about the shear maximum of the different shapes. So, for example, we have a rectangular shape, then the maximum shear or the shear stress profile would be something like this. It's a parabolic. Okay, and we have this average stress in these hidden lines, and the maximum shear max can be computed using this equation, or it can be simplified to this equation. It's just simply the V, the internal shear force, divided by A times 3/2. Okay, so that's the equation for the shear max. For a circular cross section, the stress distribution would be different, would not be really this perfect what is this perfect parabola, because it will look something like a bell shape, right? Then of course there's going to be shear max and there's going to be a shear average. The equation, the simplified equation, is just 4/3 of the internal shear force divided by the area. Okay, for a hollow cylindrical portion, okay, it will be 2V over A, and for an I-beam, for an I-shaped beam, the shear stress profile for an I-shaped beam is also different, and it was found out or observed that most of the shear stresses is being carried by this web portion. Okay, so this part is called the web, and this part is called the flange, and also this one is the flange. And even in C-shaped sections or angles, the flange, the assumption or the observation is that it carries only little shear stress, so much of the shear stresses are being carried by the beam. Okay, so the profile would look something like this. Okay, so you see there are difference in the stress profile for different cross sections. Okay, and the shear max for this is approximately taken as the internal shear divided by the area of the web only. Okay, so when we say area of the web, it's just this area. Okay, so it's not including the flange area. Okay, so that's for the shear stress distribution. And also we need to also take note about the limitations of the equation, limitations of the shear is equal to VQ over IT. We also need to take note of the limitations of these equations, because if we apply this equation to to situations beyond its limitations, then that means we'll get an erroneous result. So take note that this is valid only for beams of linear elastic material. So that means that elastic, when you load it, it deforms, and the deformation is linear. And if you unload it, it goes back to its original shape or position. Okay, and that's the first one, and it should be prismatic. So take note, prismatic. I was wrong with this. I interchanged this to non-prismatic. So when I say prismatic, it's a constant cross section all throughout the length. And for the third one, if for rectangular beams, this is only accurate enough, or depends upon the height to beam width ratio. So what that means, if this is our height, this is our width B, so that depends upon the height to width ratio. So if it's something like this, a rectangular, then it's okay. But if the ratio becomes something like a square, then it gets less accurate. Okay, so that's what our lecture handles is referring to, and of course taken from the reference text. And also, okay, also not applicable to Okay, not applicable to triangular shapes and semicircular shapes. Okay, so it's not applicable. We're not going to get any probably accurate results if we apply this formula to these shapes. So in our lecture handouts, also taken from our reference text, there's these figures, figure 7-6, some notations for the shear stress formula. So to avoid the misuse, then just take note that the edge of the cross section should be parallel to this axis. Okay, so that's one. And for the case of circular cross section, it's no longer parallel, but shear stress distribution, there's gonna be difference as well. So the shear stress should be always tangent, okay, tangent to the edge, and that's why we have a different shear stress distribution if we compare the circular cross section and the rectangular cross section. Okay, and another one is that the shear stress distribution across the width must be uniform. So what that means is in this width, the shear stresses here must be uniform. And right here, let's say here's our shear stress at this width, then all of the shear stress here must be uniform, or the shear forces. Okay, and another one is the figure 7-7. So just recall that from our topic in fundamental of stresses and strains, that for example, if here's our beam cross section with shear stresses, then if we cut a section at the midpoint, so what we get is a shear stress right here, right? But if we take a look at the infinitesimal element or the stress point, what we see is a complementary shear stress. So here's our shear stress that's seen if we cut a section perpendicular to the longitudinal axis. But the reality is that there's also shear stress that's acting like this. I mean, if we draw in 2D, if this shear stress is right here, then there's going to be another shear stress at this point, or in this phase. And for equilibrium purposes, or actually the equilibrium equation necessitates, and it is found out that there must be shear stress as well in this, just to obtain the equilibrium. Okay, so just take note of that. Okay, now we are going to solve or we're going to have a sample problem regarding this shear stress. Okay, so this problem is taken from the book by Phil Pott, and this is example 9.2, page 331. A 10 feet long simply supported laminated wood beam consists of 8 1.5 inches by 6 inches planks glued together to form a section 6 inches wide and 12 inches deep as shown. So here's the cross section of the beam. So we have these planks right here. That's the width, the height of this plank with respect to this position is 1.5, and this width right here is 6 inches. So if they are glued together, because it's 8 pieces of planks, then the resulting cross section would be 6 inches by 12 inches. Okay, and the beam, it says here, the beam carries a 9 kip concentrated load at the midspan at section 1-1, and the 9 kip concentrated load at the midspan, and at section 1-1 or AA, let's just write AA, located 2.5 feet from pin support A, determine the following: the average horizontal shear stress in the glue joints at B, C, and D. Okay, so here it is. So here's our B, here's our C, and here's our D. and the section AA is 2.5 feet from pin A. Okay, so we are going to determine the shear stress right here, and we are going to evaluate the stresses at point B, C, D, and also the maximum horizontal shear stress in the cross section. Okay, and the horizontal, as we know, since this is a rectangular cross section, the horizontal, the maximum would act in this mid span, or at the centroid. All right, so let's dive into the computation. So solution is, first we need to determine the internal shear, right? So we are going to draw the shear diagram based on these conditions, support conditions and loadings. And actually, it's just, okay, let's just write here, determine the shear force at section AA. And if we have this loading diagram, here's our beam length. And since the loading is at the midspan, this is 9 kips. So when you say midspan, that's just half from this point or from this end, and another half from this end. So that means that this load is just being distributed equally. So we'll get 4.5 kips right here at the support, and right here is also 4.5 kips. So therefore, if we draw the shear diagram, what we get is, okay, we have a concentrated load. It says go up, and at the midspan, it says go down 9 kip, and it's gonna be like this. And if we cut a section right here, 2.5 feet, and let's say this is 2.5 feet, actually the value of shear right here is just, so V is just equal to 4.5 kips, right? Okay, the next parameter that we are going to find is the moment of inertia. So solve for the moment of inertia, because here's our working equation. Our working equation is shear is equal to VQ all over I T. We have this, and now we are going to solve for this, and later on for the Q and the thickness. So for the moment of inertia, if from this cross section, this is Y and this is Z, right? So therefore this will be X, and this is our Y. Okay, so that means that our moment of inertia will be taken along the Z axis, with respect to this specifications, or this given position and axis orientation. Okay, so this will be IZ is equal to 1 over 12 base times height cube. This 1 over 12. What's the base? This is just 6. So 6 times h, 12 cube, and what we get is 864 inch to the 4th, right? So now, okay, let's use another sheet. Okay, so, or I think this is number 3, to solve for Q. Okay, so solving for Q for points B, C, D, and at neutral axis, because this is where the maximum shear stresses occurs. Okay, so in order to solve this, I just would like to draw our cross section. We have 1, 2, 3, 4, right? And we have this, and another 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, so I draw four cross section because this will represent the point B, point C, point D, and the neutral axis. Okay, so since this is a plank, then here's our let's say we have four planks on top of the neutral axis and four planks at the bottom. Okay, so for point B, here's our point B. We are referring to the stresses right here. Or let's look at first the centroid. So from the neutral axis to the centroid. So here's the centroid of this cross section, because that's what we're solving for point B. And this distance right here, this is the y bar. So that since this is 1.5 plus 1.5 plus 1.5 plus half of 1.5, this is 5.25, and this is for point B. And for point C, so for point C we have four planks again, and so for point C, where's our point C? It's right here. Right, so the area that we'll be considering is this area above this point. Okay, and the centroid, sorry, the point C should be right here. So sorry about this. This must be right here. Here's our point C, not this one. Okay, so where's the centroid of this area is right here, and the distance from the neutral axis to the centroid is just equal to 3.75. Okay, because we have the thickness right here, it's 1.5 inches. Okay, and what else for point D? Now for point D, it's referring to the planks at the bottom, and it says here point D is right here. So therefore the area that we will consider for point D is any area, or the area below this point D point, this point D. Okay, so the centroid of this area would be right here, and the distance, this is y bar, is equal to 4, because we have 3 planks, this is 4.5 inches. Okay, inches and inches right here. And for this, for the maximum stresses, then we are going to consider this area. Okay, so this is the area, and this is actually the thickness. This is our thickness right here. Again, the centroid would be right here, which is just what is this? Y bar is just equal to 3 inches. Okay, so now that we have the Q, then what else do we need? Actually, we don't have the Q yet. This is just an illustration for the Y bar and area considered. So therefore, Q is equal to area, right? Area times the Y bar. So for Q sub B, this is just, by the way, area is just simply 1.5 times 6. Sorry, this area is actually changing because that depends upon the point. So Q sub B is, we have 6 times 1.5 for the area, times the distance, the Y sub B, this is 5.25, and we get a value of 47.25 inch cube. Okay, and for Q sub C, we have an area of 6 times 1.5 times 3, because we have 3 planks, times the distance of 3.75 inches, and this is equal to 101.25 inch cube. And Q sub D is equal to the area of 6 times 1.5 times 2 planks, and the distance is just 4.5, and this is equal to 81 inch cube. And for the neutral axis, we have an area of 6 times 1.5 times 4 times the distance, which is 3 inches. So this is equal to 108 inch cube. Okay. Okay, so therefore, what else? Now we have all the parameters that we need. Then we can solve for the shear stress. So solving now for the shearing stress, shearing stresses. So shear stress is equal to VQ all over IT. That's our working equation. So the shear stress at B is equal to, what's our V? That's just 4.5, and our Q is 47.25. Okay, and by the way, the units would be 4.5. This kips. This is in kips. That means kilo in pounds. And we can also convert this to PSI later if we have a small value because of the divided by 1000. Okay, so 4.5, 47.5. Then the I, the moment of inertia, is equal to 864. That's inch cube. And the thickness would be this thickness. So this is 6, and the value right here is 41 psi. So it should be KSI, but because of the value, smaller value, then you just have to convert this to psi. Okay, and for shear sub C, we have 4.5 times 101.25 divided by 864 times 6. Okay, what you get is 87 psi, right? And for shear sub D, and shear at the neutral axis, okay, you just have to substitute all the values, and what you'll get here is 70.3 psi, and right here is 93.75 psi. Okay, so I guess that's all, and in the next video, I think we'll do one more problem regarding this shear stress. All right, so see you in the next video.